אוקיי, זה קצת מוזר שיש פה כמות מצומצמת יחסית של סטודנטים, אבל זה לא מענייני. Let's do a recap. I want to start today a new subject, the final mathematical subject before going to Einstein's equations. Before that even. So tomorrow, Monday, we said that 3 o'clock there will be another tutorial. Monday, this will be 10, 15 tutorial. Just to make sure, I do not consider this to be extra or anything. We've lost a lecture because I was abroad, so I have to compensate for that lectures. And compensation is done in the way that instead of Thursday that there was supposed to be a tutorial, I'm giving a lecture, and then Monday there is a tutorial. Now I understood from people who were here that only it was last week and this week that this Monday is free.
Yes.
For everybody.
After that, the seminar starts for some people.
After that, the seminar starts for some people. Okay, if these people are not planning to continue taking this course, then it's not it's not an issue for those who take it. Anyway, right now I'm planning to have this tutorial tomorrow. Then
last tutorial was not recorded. Is there a way to make sure that this one will be?
Make sure I do not know because I'm not in charge of recording, but I can ask the secretary to record. I'm not in charge of recording it. So okay, so that's announcements. So recap on what we did last time. Basically, I argued the following: vectors are directional derivatives. That enables me to generalize the concept of direction into a curved spaces, curved space-times. And then I wanted to write the physical equations. So that the physical equations consists of derivatives. So we had to generalize the concept of derivatives, and we generalize it to the concept of covariant derivatives. Say that V mu semicolon lambda, sorry, also denoted as lambda V mu, is defined as the regular derivative plus gamma mu lambda sigma V sigma. And for a covariant vectors, omega mu semicolon lambda is nabla lambda omega mu, which is V omega mu over V x lambda minus gamma sigma lambda mu omega sigma. This is easily generalized to any tensor of any rank. For any rank tensor, every upper index gets an extra plus gamma sign. For any lower index, it gets a minus sign. And I said that the importance of covariant derivatives is that it transforms tensors to tensors, which is, by the way, what rank of tensor is that here? No. 1, 1. So 1, 1 tensor, right? This is not a tensor. Somehow miraculously, this turns into a tensor. And it can, in the absence of gravity or flat space-time, this term disappears. So reduce back to normal derivative. What we're familiar with. So this is essentially what we wanted. That led us to the understanding of how we can write down an equation that is always correct in curved spaces, namely in the presence of gravity. And the algorithm is very simple. You write an equation that is correct without gravity, so in special relativity. And then every time we have an eta, change it to a g. Eta mu nu, g mu nu. And every time we have a regular derivative, we turn it into a covariant derivative. It's called a comma semicolon loop. And once we do that, according to the principle of general covariance, we have an equation that is true. It's very handy. So what we did, then we easily generalize all the physics that we have, that we know in special relativity, to curved spaces. Then I gave you the geometrical interpretation. And what I mentioned is that when you take a derivative of a vector, right, what is really a derivative of a vector, right? You take a vector at some point, so the vector v at some point x alpha, I have v x alpha. You want to take its derivative, then what you really do is you take the vector at the nearby location, x alpha plus dx alpha, vx alpha plus dx alpha. And then, in taking the derivative, you're really doing two things without even noticing them. Maybe you didn't think of it. The first is the parallel transport. So you take this vector v, which is identified at that location, and you transport it parallel to itself. We're going to discuss that today. To the same point, x alpha. That's v parallel. And then you take the difference. There are these two stages. This is the first stage, first step, and the second step. The second step is the difference. This is the derivative. The first step can result, or generally result, in change of the coordinates of the vector with respect to the basis vectors. And the easiest demonstration is just to look at the space that is written in curvilinear coordinates. And this gives rise to that term. This is the geometrical meaning of these terms. And then finally, I gave an additional equivalent definition of a geodesic, which is a geodesic is a path that its tangent vector is always parallel to itself along the path. In other words, whenever u is equal to 0, this is geodesic. For u and again, the easiest way to think of it, at least for me, is that if I'm thinking of the shortest path, right? We said geodesic is the shortest path between 2 points. Right? So my cover is turned, but if I'm thinking of the shortest path, right? Geodesic would be think that I'm flying in an airplane from Tel Aviv to Los Angeles, right? I will go the shortest path would be like that. And pen here represents the tangent vector to the space. It's always parallel to itself. Right? The airplane is not moving right or left, it's just moving straight. That is a geodesic. If the airplane was to move, let's say, like that, it could do so, but then you'd have to turn around at the answering point in order to reach the destination, which means that this is not the shortest path. Okay? By large, airplanes move along geodesics. By large, because there are other constraints, many political constraints or safety constraints. If there aren't any, they will move the shortest path because they want to save you. Simple as that. All right, now there is some nice thing about that, which again, it's generalized a thing that you've seen of how to write down gradients and divergence and curls in curved spaces or linear coordinates. But I leave that to the tutorial tomorrow because I want to move on to the next subject today. Any questions? Any questions? Yes.
When you move the vector out of path to meet the other vector, does it matter which path you take?
The answer is yes. We're going to discuss that right now. I'm going to answer that in 2 minutes. Yes.
So the question you asked for the covariant derivative of contravariant vector is a zero vector
Is it what? Covariant derivative?
of contravariant vector. Yeah, 0 to tensor.
Covariant derivative of a, no, it's a one-wanted.
No, from the second is
0 to this.
one.
I'm going to get to that shortly. All right, so today we're going to start I told you there is one more mathematical subject which we need to follow before we have the full tools needed to derive Einstein's equation. That's basically the goal of today and the next lecture. And that subject is called curvature. Actually, maybe we can start already on Thursday, Einstein's equation. So, curvature. Remember, why are we doing all that? The reason why we do all that is because I argued that presence of mass curves space-time. Right? So mass, energy, curves space-time. Before we can even talk about that, the question is, how do we know that the space-time is curved? What does it mean that the space-time is curved? Very crazy. How do we know? How do we know that a space-time is curved? Again, without getting outside of the space. Right? You can argue that, how do we know that the surface of the Earth is not Euclidean? Well, we can send an astronaut or a camera somewhere to the moon to take a picture and see that it's round. But let's say we cannot do it. Again, we are ants. Right? We're ants. We have no way of sending things outside of our space. If it's difficult for you to imagine, think of the universe as a cosmos, right? As a whole. We have no way, no technological way of sending anything outside of our own universe. How do we know if our own universe is curved or not? Any suggestions? Yes.
You can try to draw a big triangle.
You can try to draw a big triangle. The question is how big? If the cosmos is how big? Should I send it to the sun? Should I send it to the next galaxy? Should I send it to the center of our galaxy? Yeah. There is some technological problems there, right? You realize that.
For Earth
Yeah.
it works.
What?
For Earth it works.
For Earth it works, yes.
But following what one said, if we know what's a small step for us to do,
If we know what?
if we know what's a small step for us, if we like ants on Earth,
the universe, as the universe. How long is long? Sending a spaceship to, I don't know. I mean, the furthest away spaceship ever sent, right? Voyager 1, just across the solar system a few years ago. That's as further as mankind has ever reached. Okay. So yeah, we don't need to do that. We just need to be quite clever, even as ants. We just need an ant that is called Gauss that could tell us the answer to that. So yeah, for that, we now need to, I already mentioned that last lecture, but I did not really define it, and now it's time to really define it. The concept of a parallel transport. Again, this is something which you are doing without even noticing anytime, right? So the idea is very simple, right? I have a space, I have 2 points, A and B, and I have a path, it goes from A to B, whichever path, and now I have a vector, whatever V. But now I go on a trip along this path, right? I'm walking along this path, and I carry the vector with me, parallel to itself. I'm going to see in a second what does it mean parallel to itself, or if you're wise enough, you can already guess right now what is parallel to itself. Right, I'm taking the vector and I just take it with me parallel to itself. Right? Just think of it, right? I'm taking a big stick, I carry it with me, I go on a hike. I like to hike in Israel, I go and take the stick and I just carry it with me wherever I go. Always parallel to itself. Okay? Now, taking the vector, ensuring that it's parallel to itself, this is what is basically known as parallel transport. There is an issue here, which is a quite serious issue. That's an issue that I was asked. The outcome of the parallel transport, in principle, could depend on the path, right? For example, if I choose another path, this will be my path, and I parallel transport the vector, what am I going to get? What am I going to get? It will be the same result. Okay. Why? Because this is a flat space. But what if I'm thinking of a sphere? I'm on the equator. I'm going from the equator to the North Pole. Okay. Now my friend is also on the equator, but he chooses to go in a different path. He's going like that, and then to the North Pole. Carrying the vector. We both switch to North Pole. Our two vectors are no longer parallel to themselves. Is there any issue here? Not really, right? Just the way it is. So we have 2 points, right? A and B. And the outcome of a parallel transport depends on the path that we choose to take. Everybody sees that? Yeah, pretty clear. Yeah, stay there. That's a kind of anything to imagine. Now let's do it in a more mathematical way. So what is a parallel transform? What did I just say? Taking a vector parallel to itself. What does it mean parallel to itself? That the derivative is 0, right? It's not changed, right? So this is a curved space-time generalization of the idea of keeping the vector constant. Right? This is keeping the vector constant. As it moves along the path. As it moves along the path. So, now let's do the math. I'm going to erase whatever. I'll erase that. So we have a curve, let's call it x mu lambda, right? Curve is specified by some parameter lambda. X mu specifies the curve itself, right? Coordinate along the curve. So, requirement for a tensor t to be constant if it's a flat space, what do we have? dt over d lambda is dt over dx mu. Dx mu over d lambda is equal to 0. Right? That's in flat space. So, in any space, so generalize to any space. So the covariant derivative along the path. An alternative name is the directional covariant derivative. Again, you see that's a nice thing. I mean, there's nothing much that you can do. Right? It's normally it's written as d over d lambda. In some textbook, it will say it as d over small d lambda. That depends on the textbook that the preferred textbook that you like to see. I use that because I think it's easier to. It is defined as dx mu over d lambda and then nabla mu. Covariant derivative. Blah blah.
How they index it works?
What?
How they
What's my question?
When you power transform the vector, do we care about its magnitude?
I cannot hear you.
Do we care about the vector's magnitude when it's
Yeah, it's not changed.
It's not changed.
Yeah, that's the idea of Fourier transform. Just taking, I mean, I'm carrying a stick with me, and it did not change. Magnitude did not change, direction is not changed. Yeah. transport is the requirement that what?
This will be 0.
This is equal to 0, exactly. So parallel transport of a vector V along the path x mu lambda d v over d lambda mu, that's the way it's written, is, you can write it as dx sigma over d lambda sigma v mu, or dx sigma over d lambda v mu sigma. Is dv mu over d lambda plus gamma mu sigma rho dx sigma over d lambda v rho is equal to 0. That's the definition of a parallel transport of a vector. It's a mathematical definition. Yeah? Again, the nice thing, when you think of it, there's nothing else you can do. Think of it for a second, right? What else can I do? Right? Say parallel transport, I don't want the vector to change. Doesn't change, the derivative has to be equal to 0. It's not a simple derivative, it's a covariant derivative. Okay, along the path that I'm choosing. Fine, that's everything you can do. Yeah? Yeah? If we have a tensor T, same thing, right? You cannot do anything else. If we have a tensor T, parallel transport of a tensor, then it's d over d lambda of t, whatever, mu1, uk, mu1, ul is dx sigma over d lambda and nabla sigma t, mu1, uk, mu1, u. For example, dt over d lambda mu is dt mu over d lambda plus gamma mu sigma rho dx sigma over d lambda t rho nu minus gamma rho sigma nu dx sigma over d lambda t nu. This is the equation of parallel transport. We've seen this equation before. What is that? Geodesic, right? Yeah, it's not surprising, right? We said that geodesic is a path along which vector parallel to it is parallel transported. Transported parallel to itself. So again, there's nothing, everything is mathematically fully self-consistent.
It doesn't have to be zero. Want to
In the no. Parallel transport means it's zero.
Ah.
And if I want it to be parallel transport, means it's zero. All right. Questions? Now we can speak of a curvature. We got this idea, so we cover this one. Can I erase that? Let's talk now about curvature. So how do I know if a space-time is curved? Exactly. Now again, this goes back to this example of going through a path, right? So we choose a closed loop. Curvature.
How does it answer the question how big?
Slowly, slowly. So the curvature is quantified by another tensor. I'll encounter a few. This is quite important tensor. Let's call the curvature tensor. It has another name. This is also called Riemann tensor. Spell his name right? Yes. So, those of you who don't know, right? Riemann was a PhD student of Gauss. Gauss did this calculation for, I think, either 2D or 3D, or both. Then he gave his student to generalize that to any dimension. The student wrote it properly. He didn't know at the time that the universe is 4 dimensions. That's quite central to relativity that came out 50 years later. As we're going to prove shortly, we're going to get the Riemann tensor from the affine connection and the first derivative of the affine connection. How did we get the affine connection? First derivative of the metric. So in fact, the Riemann tensor is, all the data about the Riemann tensor is already encoded in the metric. Once we know the metric, we'll know the Riemann tensor. But as you're also going to see, it's quite nasty calculation. So as you already said correctly, the way we can see curvature is by selecting a path. How do we select a path? Point here. Right. So we can specify two vectors, right? Vectors are directional derivatives. We can specify two vectors. Let's call them A mu and B mu. And then I can go infinitesimal, let's say this is 0, 0. Right, so this will be, I'm going infinitesimal length along the direction specified by the vector A mu. So let's say this is delta A. Here it's 0, delta B. Then I go in the B direction. So here delta A, delta B. So I can take a vector 3. So use let's go in 3 row. Right? So use A mu and B mu. What?
Why does it close to parallel?
I can choose a path that will close. I can take my vector v, parallel transport it, and look at what I get at the end. At the end I'll get another vector, whatever. And I have a difference, right? The difference will be delta v.
Why going A and then B is the same as going B and then A? Because
I don't say it's the same.
but you say it's a closed loop.
Yeah, I can select a closed loop. I'm going some infinitesimal direction in the A in the direction of A, infinitesimal length in the direction of A. Then I go infinitesimal length in the direction of B. And then vice versa, and then the opposite, right?
Why should you return to the origin?
Because it's infinitesimal.
So it's almost flat.
It's almost like this. So you're right that if the space-time is not flat, there will be a tiny correction. If I go exactly delta A here and exactly delta A here, I'm not going to get necessarily to the same location here. But it's going to be a second-order correction, so I don't care. It'll have to be a physicist, not a mathematician.
No, but I don't understand why the correction is not negligible to the difference in V, something like this.
No, it's not negligible. Why? Because it's a second-order correction. I'm looking at the first-order terms, and the way to convince you is that I'm going to do things infinitesimally.
Okay.
Right? So we don't really need to go to the other galaxy. It's enough to look at our local universe, if of course the curvature is the same everywhere. We'll touch upon that down the line.
And this will define the curvature, or just
This will define the curvature.
one aspect, because it should. Okay.
Slowly, things will be. Right. So just. Okay, again, see, there's more than one way of introducing the Riemann. This is maybe the simplest one, in my opinion. You can choose it's a VC. VC. Okay, the idea is, okay. Now, since again, the action of the parallel transport is independent of the coordinates, depending on the direction that we choose only, but not on the coordinates that we set. Okay. Which means that the change in V, delta V, should be linear in V. That's the meaning of an infinitesimal transformation. So if I look at so the change in V should linearly depend on V. So we talk about a tensor that needs to have at least one upper and one lower index, right? Plus, it should depend on the vectors on the paths that we choose, A and B. So it should have extra two lower indexes to contract them. Yeah? Yeah. The change in V, delta V, right, should be linear proportional to V. Right? What does it mean linearly proportional to V? Delta V rho should be R with rho sigma V sigma. Haven't finished. Right. What else should it depend on? Delta V on NB on the directions. Right. Also, it should be linear when it's infinitesimal. It should also be linear. Delta V rho. which also should be linear with delta A and delta B. And depends on A and B, so A mu, B nu, so I should have something to contract them, nu and nu. Okay, logic is clear. So we're talking about what rank is that tensor? What rank is this tensor? It's a 1, 3, right? So we're talking about the 1, 3 tensor. It's a Riemann tensor. What else can we say about this tensor? Just from looking at that, without even deriving. Anti-symmetric in mu and u, right? Because if I go in the opposite direction, I should get the minus, right? So that means it's anti-symmetric. And u and u. The last line is.
Why is it tensor?
What?
Why is it a tensor?
Why?
Yes.
Why what?
Why is it a tensor?
Why is it a tensor?
Yes, and not something like the high connection, which is a tensor.
No. There's nothing. I mean, the change in a vector, right? What? It's independent. Yeah, it's independent on coordinates. Right? You don't care about the coordinates. Right? You can specify whatever coordinates that you want, right? X, x prime. The change is not going to depend on it. And you're going to end up. You start with a vector. You end up with a vector. Actually, you start with 3 vectors, right? 1, 2, and 3. 2 determines the directions, and 1 is the vector that you're interested in seeing how it changes.
So is it dependent on the coordinates of A and B?
A and B are directions. They're
Yes.
independent on coordinates.
Yes.
Right? Again,
Is there more formal?
you can think of whatever coordinates that you want, right? You can have a coordinate like that, coordinate basis. You can have a coordinate like that. Doesn't matter. The change in the vector is a change in the vector.
Is there more formal proof this why this is
We're going to get the formal definition of R. This is to give you the intuition of what's happening.
then from this definition we get that is a tensor.
It is a tensor. It really is. And we already know that this tensor is anti-symmetric with respect to the last 3 bases. So we can write down R rho sigma mu nu is a minus R rho sigma mu nu. So now I'm going to actually derive it. Again, there's more than one way of deriving it. What I just said is, okay, I can take a vector and just want to transport it. I'm going to take a shortcut. I'm going to take, rather than transport it in a full loop, I'm going to transport it along one pass to that point here, and then along the other pass. And then I look at the differences. It's going to be the same thing. So what I'm going to do, I'll transport like that, and I look at the commutator. It's really the same, it's just faster. Right? What is the commutator? The difference, basically. Okay.
Why commutator? And
What?
not just subtract the results.
I'm taking the covariant derivative along that and that, and then the covariant derivative in that direction, and then take the commutator, which is essentially a subtraction.
fraction when you try to commute
Yes.
that are commuting.
So what we do is we take a commutator of the two covariant derivatives. I mean, when you do a parallel transport, right, along the curve, it will tell you how much the vector changed along this path, right? When you take the commutator, then it tells you essentially the difference in the changes between the two paths, which is what we want. Okay, so it's not exactly, but it's at the end it is exact. Logic is slightly different. So what am I going to do? I don't know. A second. Nabla mu, nabla. The advantage is that we know how to do that because it's pretty straightforward. Taking the covariant derivative here. So if we start with a vector field which we call V rho. Okay, now there is a little bit of annoying algebra, but it's really nothing more than algebra. Maximum can happen is that I get messed up with some of the indexes. So nabla mu of nabla mu V rho is V rho nu semicolon mu. So it's a nabla mu of V rho nu is a V rho over dx nu plus gamma rho nu sigma V sigma. As I said, this is a 1-1 tensor. So I first take the regular derivative with respect to mu of that, and then I have this extra term. So I have d over dx mu of dv rho over dx nu plus gamma rho nu sigma v sigma plus, now I have a term here, so gamma rho mu sigma times what I have inside, dv sigma over dx nu plus gamma sigma nu lambda v lambda. Then I have this extra minus because this is a covariant derivative of a 1-1 vector, so I have this minus gamma lambda mu nu dv rho over dx lambda plus gamma rho lambda sigma v sigma. Okay, let's expand that. So here I have d mu v rho plus d mu gamma rho mu sigma v sigma plus gamma rho nu sigma d mu v sigma, that's the first term, plus gamma rho mu sigma d nu v sigma, plus gamma rho mu sigma gamma sigma mu lambda v lambda, minus gamma lambda mu nu d lambda v rho minus gamma lambda mu nu gamma rho lambda sigma v sigma. Okay. Exactly. Now we need to subtract everything with mu and nu exchange. Yeah? It's some algebra, but modulo some possible typos which are very unlikely at this stage. And just a straightforward calculation. So if we subtract that, we have minus mu and nu change, this automatically cancels out. Also, what do we do here?
This is in the next term.
What?
Third and fourth.
Yeah, this is lambda mu nu and lambda mu nu, they are the same, so they have to cancel.
Also the third and fourth.
Yes. And also the third and fourth. You are right. This one will cancel with this one when we exchange, so the situation is not as bad as it sounds initially. So what we are left with is nabla mu v rho is equal to d mu gamma rho mu sigma minus d nu gamma rho mu sigma plus gamma rho mu lambda gamma lambda nu sigma minus gamma rho mu lambda. Erase that.
You wrote the first term mu twice.
Gamma, just a second. Gamma lambda mu sigma v sigma. What did I do here?
First
D
term
nu.
mu and
Of course. Okay. Now this is clearly a tensor. Right? Covariant derivative of a vector is a tensor. Covariant derivative of a tensor is a tensor. So this is a tensor. So that means, although it doesn't really look like that, this must also be a tensor. This is what we call the Riemann tensor. So I have nabla mu, nabla nu, v rho is r rho sigma mu nu v sigma, where r rho sigma mu nu is d mu gamma rho mu sigma minus d nu gamma rho mu sigma plus gamma rho nu lambda gamma lambda mu sigma minus gamma rho nu lambda gamma lambda mu sigma. Okay, we just derived the Riemann tensor. Again, what did I really do here? I just looked at the commutator of the two covariant derivatives in the two paths that I choose. I did not prove that this is identical to taking Fourier transport along the full loop, but it is. What? Sorry? Yeah, but again, it's infinitesimal, so it's fine. There's no problem here. Yeah, I put a note here that the second derivative appears in a textbook by Falt. I generally do not recommend it for first reading because it's a bit more difficult. What? There's a textbook by Falt that helps. It's one of the textbooks that I gave you in the syllabus. Okay. It's quite famous, but it's not so simple. It's more, it's on a higher level. Then again, I guess the most surprising thing is that here there is nothing tensorial, right? Gamma is not a tensor. The derivative of gamma is also not a tensor. But somehow, miraculously, there is a conspiracy here that when you take these exact terms and you add them together, you end up with a tensor. There is some strange conspiracy that tells you that you can make a tensor from non-tensorial quantities here. From this definition, the fact that it's anti-symmetric with mu and nu is automatic, right? You just can see automatically that it's symmetric, right? And as we already said, to get to the curvature tensor, we need the affine connection and we need the first derivative of the affine connection. And to get to the affine connection, we need the metric, the inverse metric, and the first derivative. Actually, not the metric, the inverse metric and the first derivative. So really, to get the curvature tensor, if we know the metric, we can easily get curvature. Put it in a computer and it's easily calculated. The converse is not true. If I give you some curvature, deciphering the metric is nearly impossible. We'll get to that later on. What?
Does define the surface.
Right. Currently, we're just talking about the curvature. It's a tensor which is defined in any point in space-time.
לא, כאילו, אמרת שזה קשה לפתח מעלים את תנזורי המטריקה.
זה בלתי אפשרי.
זה בלתי אפשרי חישובית או בשביל מתמטית?
לא דבר, מה ההבדל?
אפשר להוכיח מתמטית שזה...
Theoretically it's possible. Practically it's impossible. Okay, obviously, what about any tensor of any rank? So this is we took the permutation of the covariant derivatives of a vector. We have a tensor. We're not going to prove it, but by now the answer should be quite clear to you. Follow the logic. It's not so difficult to answer. Right. From here, you can pretty much guess what's going to happen if I take the covariant derivative. Let's say blah blah rho blah blah sigma of x mu1 mu k mu1 mu l. What am I going to get? For every upper index, I'm going to get what is written here, right? R u1 lambda rho sigma x lambda mu2 k mu1 ul plus r mu2 lambda rho sigma x mu1 lambda mu3 k mu1 ul. And for every lower index, I'm going to get the minus r lambda mu1 rho sigma x mu1 mu k lambda mu2 mu l minus r lambda minus r mu1 mu k minus r lambda nu2 rho sigma x nu1 nu k and nu1 lambda nu3 nu l. So in particular, the covariant derivative of a covector lambda rho lambda sigma of v mu is minus r lambda mu rho sigma v. Right, it's pretty clear what's going on. What's happening here when I have an upper vector and I take in the commutation, the index goes to the r, and the second index will become subtracting this. It's the index of the vector, so this is dummy index. Same that I have here. When I have a minus, then the lower index would be here, and we contract it instead. The new1 goes to the r, and then the upper index will become the dummy index. Same for any index. Right? Questions? Questions? No. Okay. Now comes another part, which is quite clear to you. What's the connection between the Riemann tensor and the curvature of space-time?
What's the definition of curvature?
What?
The definition of curvature.
What is the connection between Riemann tensor and the curvature of space? What?
If it is determinant.
If it is zero, yeah.
It's flat.
It's a flat space, right? If it's zero, everywhere, right? All the components need to be zero. Right, so there is a theorem. I'm not going to fully give you the full proof because it will take about 1 hour, and you can find it in a mathematical textbook. I'll tell you what textbook you can find it if you're really interested, but I'm not going to give you the full proof because it requires a few theorems which we need to derive, and I don't think there is a real need to derive them to get the essence. So I'll just state it. I'll give you half proof. So the theorem states that a necessary and sufficient condition theorem. A necessary and sufficient condition conditions. Sorry, sufficient conditions for the metric G mu nu of x to be equivalent to the Minkowski metric Italian nu is R. Right? One, the components of the curvature tensor vanish everywhere. And two, the metric has 3 positive and 1 negative eigenvalues. Okay. Now I said one way is easy, right? So necessary is the easy part. Necessary. This I can prove to you in 2 minutes. Right? necessary. And so if we have a coordinate system in which the derivative of the metric is 0, if we have a coordinate such that a sigma g mu nu is equal to 0 everywhere, that means that all the gammas get to 0. Gamma rho mu nu equal to 0 everywhere. And also the derivatives of gamma would go to 0. So that means that the metric, sorry, the curvature will go to 0 everywhere. But what is written here is a tensorial equation. If it's true in one coordinate system, it's true in any coordinate system. If true in one coordinate system, because it's true everywhere. Every coordinate system, not everywhere, but any true in any coordinate system. Right, by the principle of general covariance, right, which means basically that's it. So that the R rho sigma mu nu must vanish. Is a necessary condition. To find coordinates in which all components G mu nu are everywhere constants. Okay, logic is doing is quite simple. The second is the problematic, to show that it's sufficient condition. Because then we actually need to construct such coordinate system. And I'm not going to do the construction here because it's doable, of course. There's actually a theorem that states that you can always find such a coordinate system for which the commutator will vanish. I'm not going to give you the full proof because just exhaust 2 hours and for nothing really. Well, not nothing, right? Mathematical proof. So the theorem, so this is necessary, right? The opposite is sufficient. You can write down that Asaf doesn't want to give you the full proof. It requires knowledge of a theorem which is known as Frobenius theorem. And it can be found by the textbook of Schutz, but not the same Schutz that I gave you in the syllabus. It's called the geometrical, what's the textbook? Geometrical method. Schutz has two books, at least 2 books. One that I gave you in the syllabus, and one's called geometrical methods for physics. So you can find the full proof there if you're really interested. I think it's also in the book by Nash that I don't remember at the moment. So again, I'm not going to prove it to you. Frobenius theorem, but believe me, it's true. So this is the theorem. This is the connection between the Riemann tensor and the curvature of space-time. Now remember that I gave you in one of the problem sets, I don't remember which one, maybe the last one. You needed to calculate. I don't know what I gave you. If I'm giving, you can write down flat coordinates in space, Euclidean space, in various types of coordinates. You don't have to write it in terms of Cartesian coordinates. You can write in spherical coordinates, hypergeometrical coordinates. So sometimes this can obscure whether given the metric, whether the metric describes a flat space-time. Because you could describe a flat space-time, but not in Cartesian coordinates, right? But now you have a foolproof way of knowing whether a given metric describes a flat. Yeah. Well, that depends on how many indices that does the Riemann tensor has. Well, it has four indices, but how many components? How many different components does it have? I don't know. How many?
6 days.
What? How many components?
6.
Why 6? Or how many values can each of these take?
Oh, okay.
What?
It is anti-symmetric, so basically.
Right, we're going to get to that, right? So how many of them are independent? First, how many total do we have here? 256, right? You all see that? In 4 dimensions. Of course, if we talk about less dimensions, it's less. Now, there are many of them are dependent. That's what we're going to do now. Many of them are going to be dependent on each other. But totally, there are 256 in 4 dimensions. You can calculate them all. If they're all 0, you know it's a flat metric. But if we talk about 2 dimensions, you got many less to calculate. All right. Questions? Again, those days, what you normally do would just go to the computer, use your favorite, I don't know, MATLAB, Mathematica, Python, whatever, and you just ask them to do it for you, right? But 20 years ago, people could not do it. Well, they could do it by hand. Questions? No? Okay, so if no questions, then let's move on. What I want to do now is exactly what we just discussed. Algebraic properties of the Riemann tensor. Algebraic properties of the Riemann tensor. So we just said in n dimensions, which is what we care about, in n dimensions, we have n to the 4. And the Riemann tensor has n to the 4 components. Now we said there is anti-symmetric in the last 2 terms. So how many independent components will have? So in these last 2 terms, the number of independent components would only be n times n minus 1 over 2. in fact, there are many other symmetries of this tensor. So let's derive a few because it's actually quite important to see how many independent components we have. Int, it's much less than 256 in 40. So again, we need to do a little bit of algebra, but it's nothing more than an algebra. So to calculate that, I'm going to look at the Riemann tensor with all indices down. Okay, so how do I do the Riemann tensor with all indices down? The only thing I can do is multiply by the metric. So look at R rho sigma mu nu G rho lambda R lambda sigma mu. Okay, let's do it. G rho lambda, again I promise you it's going to be a little bit ugly, but doable. D mu gamma lambda mu sigma minus d mu gamma lambda mu sigma plus the gamma gamma terms. Gamma lambda mu, I call it alpha, gamma alpha sigma nu minus gamma lambda mu alpha, gamma alpha sigma mu. Now I actually have to take the derivative of the affine connections, so I'm going to expand them. I don't have too many options. So 1/2 G rho lambda. Now I'm going to take the derivatives here. So G lambda tau d mu G sigma tau plus d mu d sigma G tau mu minus d mu d tau G mu sigma minus d mu d mu G sigma tau minus d mu d sigma G tau mu plus d mu d tau G mu sigma. These are the derivatives of gamma. Now I have to take the derivative of the inverse metric. That, so this is still the derivative of that. Plus 1/2 G rho lambda d mu G lambda tau. Then d nu G sigma tau plus d sigma G tau nu minus d tau G nu sigma minus, this is for this term, and now for the second term, minus 1/2 G rho lambda d mu G lambda tau d mu G sigma tau plus d sigma G tau mu minus d tau G mu. Then the last term I just got plus G rho lambda gamma lambda mu alpha gamma alpha sigma nu minus gamma lambda mu alpha gamma alpha sigma nu. Okay. The only thing I did here was to expand gamma. 1/2 times inverse metric times the derivatives. And then I just took the derivative, which was expanded twice. Once the derivative of the inner parts, and then the derivative of the inverse metric. There, told you. Ugly, but it's just algebra. Now, partial derivatives commute. So if partial derivative commutes, then I have, what do I have? Really, I didn't do anything. partial derivative commute, then this means that this part go away. And yeah, unfortunately that's it. So what I'm left right. This is g rho lambda g lambda tau, so I get g delta rho tau.
What about the second term and
Which term?
aren't they just reductive?
I have to check it out. Just a second. No. You're not. Hold on. No, this will not. Where will they go? I have different derivatives here. This is d mu d sigma. This is d nu d sigma.
Right, but if you change the mu to nu.
No, I don't change the mu to nu. Where did it?
No, oh, okay. No, I got it.
I don't change anything here.
Yeah.
So what I'm left with is 1/2 of the first line is the 1/2 d mu d sigma. Now this gives me delta rho tau. So every time I have a tau, I have a rho. So it's 1/2 d mu d sigma g rho mu. Then minus d mu d rho g mu sigma minus d nu d sigma g rho mu plus d nu d rho g mu sigma. Okay, that's for the first line. Now for the second line, I have that part which I'm going to use d rho lambda d mu g lambda tau is a minus g lambda tau d mu g rho lambda. So there is a delta here waiting. So I take a derivative of the delta, so it's a 0. So this is a minus g lambda tau. The derivative of g I can write as gamma eta mu rho g eta lambda plus gamma eta mu lambda g eta. So when I do that, I end up with these two terms. I can write them as, let's see, I told you exactly, but it's nearly close to the end. So you have a minus gamma eta mu rho g eta lambda plus gamma eta mu lambda g eta rho. So minus is here. Gamma lambda nu sigma plus gamma eta nu rho eta lambda plus gamma eta nu lambda g eta rho gamma lambda nu sigma, and then minus plus the last two terms, g rho lambda gamma lambda alpha gamma alpha sigma nu minus gamma lambda nu alpha gamma lambda mu sigma. Okay, check it out at home clearly. Slowly. Check it out slowly that I didn't do it here. I I know I didn't, but convince yourself. So we end up at the end with R rho sigma mu nu is equal to 1/2 d mu d sigma g rho nu minus d mu d rho g nu sigma minus d mu d sigma g rho mu plus d mu d rho g mu sigma plus the last term, the g. Gamma gamma g eta lambda minus gamma eta mu rho gamma lambda sigma mu plus gamma eta mu rho gamma lambda mu sigma. Okay, again, follow the algebra. That's what I wanted to get. Now we have, either you trust me or you want me to go over one by one. I hope you trust me, and if you don't trust me, just go and read it in the textbooks. Better derive it yourself. That's what I wanted to get. And but now we just have a look at that and see what it tells us. So, properties. We have symmetry under exchange of the first pair and the second pair of indices. Symmetry under exchange of pair of indices. Namely, R rho sigma mu nu is R mu nu rho sigma. If you're only exchanging one, what do we get? One? Minus, right. So we have anti-symmetry. Anti-symmetry. R rho sigma mu nu is a minus R sigma rho mu nu is a minus R rho sigma nu mu is a plus R sigma rho mu. The last term we have, I don't know if you can see it right away from here, but that's a little bit more naming, is a cyclicity in the last three terms. Permutation of the last three terms, they are cyclic. So, cyclicity, sum of cyclic permutations of the last three indices. R rho sigma mu nu plus R rho, or permutation here, so it's going to be a mu sigma plus R mu rho nu sigma mu is equal to zero. It's the meaning of cyclicity. Is equal to 0.
Derived from the second identity, or is it a different identity?
What? Each one is different.
Just looking at the round formula at the top one, and looking at change.
Just write it, add the three terms, and you'll see that everything cancels out.
Believe you.
No, do it. Don't believe me. The only thing I did not give you the full proof is this Frobenius theorem. Because everything else, and I told you where you can find it. Everything else, I don't expect you to believe me in anything. That's guys, that's a science training. You don't believe in anything. Check it yourself. From here, you can easily check that. Maybe not easily, in the sense that you might get lost in some of the indices here, but there is nothing in principle here that prevents you from just doing it. Okay, so before we go home, okay, this of course has a meaning of how many free indices Riemann tensor, also independent indices the Riemann tensor really has.
What does it give us? What does it give us? How many independent?
We're going to calculate that, but we're running out of time, so we'll do this calculation on Thursday. But there is one thing that I do want to mention before we go home, and that is that from the Riemann tensor we can make some other tensors. How do we make a tensor from another tensor? Yeah, we can do contraction. So if we do a contraction, by contracting of the first and third indexes of first and third indexes, get a new tensor R mu, which is R lambda mu lambda nu. This has a name. That's called a Ricci tensor, which is an Italian guy. Right, it's tricky, but it's really Ricci. It's an Italian Ricci tensor. Actually, I had a colleague once who told me he met Ricci. I never met him. Now the Ricci tensor is symmetric. R mu nu is R mu nu. Ricci tensor is symmetric. It's actually the only independent contraction that you can get from it, but I'm not going to prove it to you now. Now, if we use the metric, we can even have another contraction, which will be what? Scalar, right? So we can do use the metric to get what's known as the Ricci scalar R, which is R mu nu. So this is really G mu nu R mu. So from the Riemann tensor, so what did we do? Today, we did quite a lot actually. So we introduced the parallel transport. Using the parallel transport, use it last time, properly define it only today. Define the parallel transport. Using that, we introduced and defined the Riemann tensor. It's a 1-3 tensor. Then we looked at the properties of the Riemann tensor. We got 4 properties. 3 are written here, and the 4th one is the anti-symmetry in the last 2 indices, which is the easiest to show. And then from the Riemann tensor, we could make contraction to get another tensor. This is the Ricci tensor. And contracting it again, we get the Ricci scalar. All these are going to end up to be quite crucial in deriving Einstein's equation. Do we have any questions? Anyone? Yeah. So I want to remind you all, by the way, okay, first remind you all, tomorrow, so there is a tutorial, it's defined as a tutorial, not by me, given by Akshay, 3 p.m. as we said, here, same place. I will ask the secretary to make sure that it's being recorded. Again, it's not I'm not in charge of recording, I can only ask. Okay, any questions? I don't know how you feel about what's going on right now. I mean, I know there's been a lot of algebra in the last few weeks. Still have some algebra, don't worry. But then again, we are getting quite close to introducing Einstein's first equation, which will be introduced to you maybe even on Thursday, if we go fast enough. I don't want to go too fast in this course. So it's really, really, really important that you guys make sure that you follow everything we did, because it's very easy to get lost in the algebra here, and it's very easy to get lost in concepts. And I don't need to tell you that right now. It's very important that you don't want to rush. Right? If I rush, there is no point that I rush and you don't understand. Make sure that you're with me. Did I go too fast today? No, nobody's complaining. Whether I did go or not, I will see in the exam. But that's the thing I hate. Some students, they sit down quiet, they don't say anything. I'm not talking to anyone specifically, but I've seen that in person. Then it comes to the exam.
You sit sometimes to know what
Then it comes to the exam, yeah, exactly. So that's exact. No. You reach a point that you don't even know what to ask because you become too stupid. And some of you might have reached this point. That's why it's absolutely crucial that you keep very, very close to what I'm doing here. Don't wait until because things are getting more and more complicated. On the one hand, on the other hand, if you do follow, you see that there is really what I'm doing is the only thing you can do. There's nothing really. There's nothing else that can be done. That's another thing about it. It's very, very solid. So make sure that you're with me. All right. Is there any reason why some of you came late today?
It's Sunday, so Sunday morning.
Sunday, you know?
All the traffic, that's it.
I know. I also have to wake up early today to make sure that I come here on time. But I guess I don't know where you guys are coming from. But 10 o'clock is legitimate. It's not 8 a.m. All right. Enjoy holiday, write your board, and I'll see you on Thursday. And actually, I will see you all tomorrow. הפיתוח פה הוא כללי גם, לא אמרתי מאמין.